Hey everyone, it's Scott from Redmond Tutoring.com, and in this video I'll show you some great and easy tips for solving a problem in which a charged particle moves through an electric field. This was an actual test question from my class. The idea is to deflect an electron coming in from the bottom left at 5 × 10⁶ meters per second to the right so that it will swat a fly located at the top right corner of the diagram. There may be simpler ways to swat a fly, but that doesn't matter much when you see a question like this on your test. There are 4 parts to the problem. First, determine which plate is positive and which is negative. Next, my students had to draw vectors for the acceleration and force on the electron and for the electric field between the 2 parallel plates. Third, they had to solve for the actual electric field, and finally, they had to find the potential difference between the plates. Part A is fairly straightforward. The electron must be deflected to the right to hit the fly. Electrons are negative, so they're attracted to positive charge and repelled from negative charge, so the right plate must be positive and the left plate must be negative. The other way wouldn't work. Part B is also kind of easy, and my approach gives a key tip for working with these sorts of problems by relating acceleration, force, and electric field. The acceleration can only be right or left because the electric field can only be right or left, and the problem requires that the electron accelerate to the right, which is along the positive x-axis. Since F is equal to ma, the force must also be to the right. F is also equal to QE, so E is equal to 1 over Q times F. Notice that these equations are in vector form, and also notice that the electron has negative charge. Therefore, the electric field must be in the opposite direction to the force, so E is to the left. These directions match what I'd expect from parallel plates of opposite charge. The electric field goes from positive to negative. Here, that's to the left. F is equal to QE, and since Q is negative, F should be to the right. Force causes acceleration, so acceleration is also to the right. Going from E to F to A matches what actually happens. The electric field causes an electric force to act on the electron, and that force causes the electron to accelerate. I highly recommend that you quickly draw these directions for acceleration, force, and electric field on your own test problems. It very quickly helps you get the right answer and shows that you know what you're doing. In Part C, there's some math. The strategy is to first find the acceleration using kinematics, second find the force using F equals ma, and third find the electric field using E is equal to 1 over Q times F. First I'll do the acceleration. This requires some kinematics, so I'll write out what's given and what's unknown. Delta x is 0.20 minus 0, v initial x is 0, v final x is unknown, the acceleration on x is unknown, and delta t is unknown. Delta y is 0.50 minus 0, v initial y is 5 × 10⁶ meters per second, v final y is also 5 × 10⁶ meters per second, since there is no acceleration along y, and delta t is still unknown. First I'll use the constant velocity and known displacement along y to solve for delta t, 1 × 10⁻⁷ seconds, and use that along the x-axis to solve for the acceleration on x, 4 × 10⁻13 meters per second squared. Ay is 0, so the vector a is 4 × 10⁻13 I hat meters per second squared. Next, find the force. F is equal to ma, where m is 9.11 × 10⁻31 kilograms for an electron, and I just solved for A. This gives me F is equal to 3.6 × 10⁻17 I hat newtons. Finally, find the electric field. E is 1 over Q times F, where Q is negative 1.602 × 10⁻19 coulombs, and I just found F, giving me E is negative 227 I hat newtons per coulomb. Done. Your prof is likely picky about specifying the direction because the electric field is a vector quantity. That's where the I hat notation comes in very handy, although you could just say 227 newtons per coulomb to the left. Alright, Part D. This also has a small bit of math. The potential difference for a constant uniform electric field can be found using delta V is equal to negative E dot delta S. I just solved for E in vector form, so I just need to find delta S, which is the displacement. The electron moves from its initial position at the bottom left to its final position at the upper right, which is 0.2 meters along I hat and 0.5 meters along J hat, so I can substitute that into the expression for delta V and solve for delta V is equal to 45.5 volts, going from the negative plate to the positive plate. You may notice that the y component of displacement, perpendicular to the electric field, contributes nothing to delta V. Awesome. And that's it. The problem has been solved. I'm Scott Redmond, and I help students pass physics. I hope this was helpful to you. For a transcript or more information and grade-boosting physics tips, check out the link in the description box.